Well, hello everyone, and welcome back to Adrian's Digital Basement. We're back on the Brazilian Apple II clone, and this is part 3 in the series. And I recommend checking out the first 2 parts if you haven't seen those yet, because as per usual with these repair sagas, which this definitely is, I'll be continuing where I left off in the last part. As a quick recap, in the first video, I took a look at the computer itself, a little bit about the history of the Apple II clone scene in Brazil, and then we started taking a deep dive look at the motherboard. And it turned out that this thing, which wasn't showing any signs of life, had a bad buffer transceiver chip off the CPU, which was keeping it from working. But even with that, and I could see signs of life on there, this thing was still not really working properly. So it was in part 2, I really dug into this thing to try to find out what's going wrong, including writing a custom diagnostic ROM to help me diagnose what was going on with this thing, because I could tell it was running code, but it wasn't actually updating the screen, it wasn't beeping the speaker, it really wasn't showing any signs of life. So it turned out there were a couple problems on this board. There was a bad connection in one of the sockets that has to do with the text mode, and then there was a bad trace. And finding that, of course, whenever you have bad traces on motherboards that aren't caused by, say, a cut or a break, but a manufacturing defect, can be really difficult to find. So I found that in the last video and got it working, and this motherboard started running diagnostic code. Well, what I didn't end up doing in the last video is running any actual software on here, say Apple DOS and games and stuff like that. So we're going to start off in this video by doing just that, because I think running actual software on this will show if this thing has other faults, which I'm pretty positive there are numerous other faults. But very quickly, running software on this thing will require one other component to be working, and that is the keyboard. And this keyboard, which is a clone Apple II Plus keyboard, doesn't really follow any kind of schematics of the original Apple II keyboards. And let's just say that getting this working, it's going to be a lot of work, including reverse engineering of half the circuitry on here, so I could really understand what was wrong with it so that I could get it working. So grab yourself some popcorn and watch me struggle to try to get this motherboard working again, and then get this keyboard working again, and then, well, let's just say at the end of this video, everything kind of goes downhill very quickly. Yeah. So without further ado, let's get right to it. In part 2, where I finally got this thing to behave correctly with the diagnostic ROM. So one thing I never did is I never actually put the original ROM back in to see if this thing boots into AppleSoft Basic. I noticed when the computer started finally working in part 2, the colors that were showing up on the Apple II dead test ROM didn't quite look correct. So I definitely think there are some issues with the video output circuitry on this. It's nothing that will keep the computer from working. I'm very confident that this computer will just work, and it will actually load software off floppy disk as well. But I'm definitely seeing some issues relating to either the color burst or something around the color circuitry that's on here. Not to mention, if you recall from part 2, with the RetroTink set to component input, I also had some video problems where the image was really blown out. I think that was because of a spurious sync pulse that was in a spot that it shouldn't be. Either way, I think the first thing we got to do is, well, I have the original ROM back in there anyways. Let's plug in the speaker. Let's get this thing powered up and see if we just have a normal sounding AppleSoft Basic beep. 3, 2, 1. Well, that doesn't sound right, does it? Let's see what this is actually doing on the video. There's a few things wrong with the video right off the bat. And again, this has nothing to do with this crashing that's happening right now, but at least it has to do with the video output circuitry. First of all, there's that dark black line on the left side, just to the left of the asterisk and the 5, goes all the way from the top to the bottom of the screen. That is that's that spurious sync pulse or whatever that is affecting the way that the RetroTink at least adjusts the brightness. Well, without the keyboard connected, I can't easily reset the machine. So let's reset it by power cycling it. It does just crash. This could be a bad connection in one of these ROM sockets. That is actually what I'm sort of thinking. So I'm just going to wobble these around in here. We'll power cycle this. I did dump these ROMs, so I know that they are correct. There we go. Yes, it was just a bad connection in one of these ROM sockets. So the fact is the F0, F8 ROM, this one here, it's number 3, this is the boot ROM. That's enough to kind of get the system initialized. But then AppleSoft Basic itself is running inside of these 2 chips. And if these have a bad connection, then it's going to jump to one of these and then, crash like it was doing there. So let's just power cycle this again. In fact, I'm going to kind of like bend the board a little bit, bang on it, see if this makes a difference. No, we're good. We're working. Now, as for that initial power on weirdness that was going on, I didn't have a video hooked up, so we couldn't really see what that's doing, but I might have to kind of let this machine cool down a little bit to kind of go from there. I fully suspect that that is probably just a bad connection in the reset circuit, most likely, which I think is this area right here. This is a 555 timer, and I think this chip is responsible for reset on the machine. So maybe the reset line was just kind of going wild a little bit up and down, and oscillating, and that was causing that weird beeping thing we heard. Now back to our video problem. So besides that vertical line that shouldn't be there, one of the other issues is that we have color fringing around the text. Well, the way the Apple IIs work, except for maybe revision 0, all the later revision motherboards should have a color killer circuit. So while you're in text mode, there should not be a color burst generated. And the color burst is what tells your video display, so the RetroTink in this case, but even a monitor would be the same, to activate its color decoding circuit. Well, we don't want artifact color running while we're in full screen text mode, and I have a feeling that that part of this motherboard is also not working. And maybe that's also related to the vertical line that we're seeing in the video signal, which is also messing things up. I think the best thing for me to do is put a disk controller in here and let's load up some software that has some full screen color graphics, because I want to see as well what the color looks like, because I have a feeling that we're also going to be missing the orange and the blue colors. They're not going to work properly. Now, actually, the funny thing is, thinking about that, is the revision 0 motherboard of the Apple II, the very first one, didn't have those colors, and it also didn't have the color killer circuit that disabled the color while in text mode. And I wonder if this clone somehow is a clone of the original revision 0. I mean, it doesn't look like it is, because there's other parts of the motherboard that are definitely different, but maybe this is an amalgamation of different revisions, but it includes the video circuitry from that original Apple II revision 0, which could explain why the color doesn't work quite right. So let me get this card plugged in, and I happen to have brought a floppy drive, so let's get this connected up as well. So let's put that disk in there, and let's see if Fat City loads. It's loading, that's normal. This is a Franklin 10 disk drive. I think it's a sugar art mechanism in there. Okay. Well, I guess, okay, few things I'm noticing there. The music didn't sound like it was at the right frequency. So there was that. And then also our colors are wrong, but this is the color trimmer pot. So let me try adjusting this color trimmer here and see if that has an effect. I mean, it does change the color. We are without a doubt missing the high-res half pixel shift, which would give us the blue and the green color. It's the extra top bit of each of these little chunks of high-res graphics that shifts it over by a half pixel. That was Woz's little invention that gives the Apple II 2 additional colors in high-res mode. Just so you can see the actual way this should look, I plugged in the Apple II VGA card, and let's boot the software. Okay, so that's how it looks. Sky is blue, the words Fat City are in orange. Switching back to our other input, it's too slow at switching. Oh, there you go, you saw a little bit of it. And the same thing that's going on here. Choose your keyboard for joystick. That should all be orange. And then the dots around the background there, around those words, that should be in blue, like this. Okay, I think what I need to do is we need to boot some different software. So this is Locksmith 6.1, which is a text mode utility. Just want to make sure that the color killer stuff is absolutely broken. So that's how it looks. Of course, the text should look very similar to that when we go through the composite video. But there you go. You can see we have a ton of color fringing. Now, one thing I'm wondering about here, maybe the issue, and this would also explain why the sound is weird, maybe the issue is the crystal oscillator that's on here is not running at the 14.3 whatever megahertz that the normal Apple II crystal runs at. This is a master oscillator. It's right over here. Could be they switched this out to be, well, more appropriate for the TVs that were in the Brazilian market. There's no way NTSC artifact color would have worked in Brazil anyways, but perhaps they got it closer by changing the crystal out. And I wonder if this little variable capacitor here has something to do with the speed that the master oscillator runs at. I know if I turn this, we get strange color fringing. And you know the weird thing is about the color fringing we're seeing right now is, notice how it looks like it's in diagonal bands. And that would be an indicator that our clock speed is just way too far off. And turning this, it sort of locks in there. but I almost feel like it's still giving us sort of diagonal stripes. Now running any kind of diagnostics in this thing, which I just put a disk in there, I'm going to have to plug a keyboard into the computer. Pretty sure in other tests under number 4, we actually have like a full screen graphics test with the different colors and stuff like that, which is really what I need to get to. But I do need a keyboard, and I have no idea if the original keyboard works. So I guess this is good enough a time as any to test it out. And if this keyboard is broken, I can take apart one of my Apple II Pluses and steal the keyboard out of that. I'm positive that the interface on here is exactly the same for either one of them. Right, so a few things I need to fix on here right off the bat is this disk capacitor is no longer connected. So let me try to repair that first. So this side of the capacitor was disconnected, so I cleared that out, resoldered it. But then this side, the joint was actually broken. It ripped off the PCB. So I put a little jumper link here that reconnected the floating one. This is no longer connected to the trace right here, this trace, and it is connected to those 2 pads, and then that was already there. I forgot this keyboard also has a broken space bar. I mean, the switch works, which I think is this right here. Well, I don't know if the switch works, but you can actually push the space bar. Oh yeah, okay, that's working. And look, we have less than 1 ohm, so that's actually good, that switch. I assume these are jumper links. There's little 4 points here, but these are switches. So we'll try this one over here randomly. Oh, well, it was working because I was pushing it down by pushing the keyboard down. So it's quite possible this thing actually works. I mean, 2 switches work at least. So this thing was just floating around inside the case, and the pins are really mangled. But I put that little piece of foam on there just to try to keep it from getting worse, at least. So there are those pins. They're not corroded. They look like they're gold coated as well. All right, so if you don't know how to hook one of these up, the way it should work is that the stripe should be pin 1. So that would be pin 1 right there. And if you look at all the other chips, there's a dot for pin 1, which happens to be the lower left corner. So therefore, this should go on like that. Now, before I power this up, though, what's going to be important is to just double check we have continuity between, say, the ground and 5 volts on these TTL chips and the ground and 5 volts on all of these TTL chips. Because in case this is wired up backwards for some reason, which I don't think it is, because if we look here, this is pin 1 and the stripe is right there, which makes this pin 1 right there. So yeah, it looks like this is wired up correctly. I think these are pretty dirty and crusty, these sockets, so this thing may not work right off the bat. But I suppose it just won't hurt to just try and see what happens. I'm going to take the Apple controller out so we can just end up right in basic. Just double checking everything else looks okay. All of these are in the correct orientation. Nothing else damaged, it's just really dirty, but I don't know. Let's give it a try. All right, we're booted. All right, well, nothing works. How about reset? That doesn't even work? Oh, control reset does. So that tells us that at least it's hooked up in the correct orientation. It seems like no other key is working, and I know the spacebar works. We measured it on the multimeter, and I was getting good continuity there. So we should have some signs of life on this thing. So the way the keyboard works on the Apple II is actually plugged directly into the data bus, well, through some latches and stuff like that. So there's a strobe signal that comes from the computer that tells the keyboard, hey, latch the actual value of whatever key was pushed, if there was any, to the computer, and then the computer picks that up on the data bus. It's hard to know right now where our fault is. I mean, I definitely know that control reset, which just happens to be a separate pin on this, is working, but we don't know, well, if the rest of this is working. We saw that there was going to be 5 volts on this thing, so those chips should be powered up. But is anything actually happening on here when we type keys? Well, let's just scope it and see what happens. I mean, before we do that, I guess what I can do is I could just try pushing on these chips in the sockets here a little bit. It's just sort of the easy thing to do. It's so dirty and crusty, this whole thing, that I'm very concerned that, I mean, it's worse than the computer, that's for sure. This is so bad. Same exact type of sockets that are on here as on the computer. Maybe what we'll do is we'll just use a toothbrush here with some deoxit already on there, just to clean it a little bit. It goes without saying that for ultimate reliability on this computer, every chip really needs to be taken out and the sockets cleaned and some deoxit put in them. There's just so much tarnishing because of the conditions that this thing was stored in. That's quite like that random intermittent problems are going to kind of be a continual problem for this thing. I can't believe how tarnished this is. Like, could that really have been making good contact in that socket? Especially look at these pins over here. What I'm going to do is I'm going to read this chip out just so we can have a copy of it. Pin detection error. Is this chip bad? It just could be that there's no contact. Now, if I try to read this with the chip removed, we get a whole lot more pin errors. Looking how tarnished this is, I'm going to try cleaning this up first. All right, so it's not perfect, but it's better. I didn't want to go too heavy on this because you could start to get down to the copper, but at least there are some shiny-ish parts there, and there's deoxide on here right now. Let's see if the read works. All right, a little better, a little better. I'm gonna move it around in the socket here. Retry. So it's 7 and 9. Oh, 7 and 10 last time. Let me push on it. Oh, there we go. Got one read out of it. Oh no. Oh no. Nothing on it. Are you kidding me? Well, that's not going to result in a working keyboard, that's for sure. Oh no, it's like it's blank. Okay, I'm just going to try something. I put it into a socket and I stuck it into the programmer. Maybe this will kind of wipe the pins a little bit better. Maybe. Oh, look, data. Oh, this is good. Now what we can do is I can do a verify pass, which just reads back the chip from what's in the buffer just to make sure that it's good. So what I've just done is I've saved the EEPROM, so just in case, and then I'm going to like wiggle it around in the socket and just see if the data changes at all. So I just wiggled it. Now we do a verify pass, which is going to compare the buffer to what's on the chip. Oh, good. It looks the same. Excellent. Excellent, excellent, excellent. I was really worried there for a second. Okay, well, let's put this back in the keyboard. Now, one thing is that these round pin sockets don't fit in these SMK sockets. They really only work with the flat IC pins. So I can't even use a 1ROM, for instance. I think the other types of sockets would, but I just don't have any. All I have is these round type here. But let's do the same process again where I deoxit this socket and then rub it quite a bit. And then the chip goes back in like that. And let me do these other two chips here. This one here is a latch. I think this is a latch. And this is definitely responsible for sending the data from the keyboard down to the motherboard. Not nearly as tarnished as that. Oh, but the socket is a normal one, like a dual wipe type, and it's a little messed up when I pulled the chip out of it. So this one might need to be replaced. And I hate reworking these kinds of boards because they're very fragile. But this might be okay. Just push it in there like that. Oh, there's a little dead bug under there. Something from Brazil, I guess. Something with stripes. So I can be pretty confident saying that I doubt that that chip was making any kind of contact in that socket, the EEPROM specifically. And that would result in the keyboard just not working at all. This chip here is not that tarnished. It's just that EEPROM was unbelievably tarnished. Let's see if that made any kind of difference. Darn it, still not working. I will say that the caps lock key has an LED on it, and the LED is on. So that means this thing is getting power. So we have connectivity up to this. But the problem is now is it's hard to know if the problem exists on the keyboard, like I said, or the motherboard still, even though I've reseated these chips. And unfortunately, when you have a machine like this that has so much corrosion all over everything, it's just so hard to know where our issues are. Now, I could easily just go grab another keyboard and we can test a known good keyboard on this machine, and then that would tell us if the motherboard's the problem or the keyboard. But what if you're working on a machine where you don't have spare parts? Like you only have one Apple II and it's this one, and you don't have a way to swap parts out. Swapping in known good parts is obviously a quick and easy way to figure out, well, where the problem lies, but that doesn't really help you understand how to troubleshoot something when you don't have the ability to swap parts. What if this was like a bespoke system that used a unique keyboard and motherboard and I just had no way to swap it? We would have to troubleshoot to figure out where the problem lies. So that's what I would like to do right now. And I'm going to use the oscilloscope and we're going to start probing around on the bottom of this keyboard when I type stuff on it. And I'd like to see, are we getting the strobe signal, I think, which comes from the motherboard? I think that's how that works. And then are we getting any kind of data sent back to the motherboard? As far as the motherboard knows, we're not typing anything. As per usual, I'm going to be going from Apple II Circuit Description by Winston D. Gaylor. This is easier to look at schematics-wise than the original schematics that came, or at least are available on the internet for the Apple II. They're like these scans that are just kind of impossible to follow, just all these huge traces and multiple pages, and they're cut. The Apple II Circuit Description does have schematics for both of the keyboards that were on the Apple II and the II Plus. One, I think, is called the Datanetics keyboard. It's a one-piece keyboard. and the other one is a two-piece keyboard, meaning it has a matrix that's connected to a small circuit board that then is what connects to the motherboard. This is the two-piece keyboard, so the keyboard matrix itself can be from multiple different manufacturers, but the electronics section is on a separate little board you can remove, troubleshoot, and reconnect. Now, the way that the Apple II keyboards communicate with the motherboard are going to be the same as the way this one communicates to the motherboard, even though the electronics that are on this keyboard are completely different. So that's all that really matters, is we take a look at the pinout that goes from the keyboard down to the motherboard, just to make sure that we see the appropriate signals on there. Now, earlier I misspoke that said that the strobe is actually an output from the keyboard that goes down to the motherboard. It's this pin 2. And then we have bit 1 through 7. We'd have to go find the motherboard side of the keyboard schematic somewhere else just to see how this pinout relates to what goes into the data bus. But I'm assuming that B1 is actually data bit 0 and B7 is data bit 6, with data bit 7 not being hooked up. And that's because the Apple II and the 2 Plus don't natively support lowercase, although this two-piece one does have a lower uppercase option. The way it encodes lowercase, if you do have one of these keyboards, you can install a toggle switch on it and then switch into lowercase mode. It's not totally useful because when the lowercase mode's enabled, it doesn't work like you would expect where you hold the shift key down to get the other case. It's like all lowercase or all uppercase, and there were some other issues as well that make it kind of impossible to use. But generally, I think this is good enough for us to see what our signals should be. So we should have a strobe signal coming out on pin 2, 25 microseconds, and then we should have some kind of data that's also pushed out at the same time where it goes high for those particular keys we're pushing. We can also see right here that pin 1 is 5 volts, pin 8 is ground, and pin 15 is minus 12 volts, which is used with this keyboard controller on the two-piece keyboard, not going to be used on this one. Starting on pin 1, we have very noisy 5 volts, but it's there at least, it's there. Pin 2 is our strobe, and absolutely nothing is happening for that. So that would explain why we don't have any activity at all on here. Now, we could easily just have bad connections. This whole thing looks just horrible. But if I follow pin 2, it goes over to this IC, and I'm pushing keys and we're getting nothing. So we're not really getting much signs of life. I think our problem mainly is going to be the keyboard itself. I think what I'm going to have to do with this thing is I'm going to have to try to figure out and maybe reverse engineer a little bit about the way this works. Because right now I just don't really see any activity on the keyboard, and I'm pretty sure it should be doing stuff when I type stuff. So bad contacts, bad chips, something's going on here. And obviously with our CommTech keyboard, I have no schematics for this. Luckily, it's a single-sided PCB, so I can just take a picture of it, but I still need to try to figure out how this is working. All right, so here's the keyboard. I've done a little bit of work in GIMP overlaying the back and the front side so I can see the chips and the traces and whatnot. It's really hard to see these little links they have here. These are a way to jump like this signal up to this signal. Because it's a single-sided PCB, they decided to use these little stick-on things. Hopefully these are working. Anyways, looks like what we have is the keys are hooked up to address lines on the EEPROM, along with stuff from these two Motorola chips. Now, for a keyboard to work, you have to have some kind of scanning, something that is constantly counting and going through, well, all the keys in rows and columns and things like that. And look at these chips, there has to be something that does the scanning. We need to start there to make sure it's actually running. It's this chip right here. It's a MC14017. We look here, it's a decade counter. Now this chip, for it to work, requires a clock, an input, I'm pretty sure. So yep, there's our clock. And we need to see if that clock is good. I don't know where that comes from. It must be generated on this thing with these capacitors or whatever. And maybe that's our problem. So we need to start there, this clock input, pin 14 on this chip. And I guess there's a clock enable and a reset pin. So first we'll power up the computer, make sure I have everything hooked up correctly and nothing is touching it. Yep, there we go, we got the beep. All right, here's pin 14. Well, that's a problem right there. There's no clock. So clock is 14, clock enable pin 13. That is low, and that should be low for it to work. And then we have pin 15, which is reset. I don't know if it should be low or high. And then that is pin 16, which is going to be the power input. It's not listed on there. Oh, it does say it. VDD pin 16 and VSS, that's ground, pin 8 over here. Okay, those look fine. But we have no clock. So that's going to keep this from working. And I'm touching, by the way, on the socket itself, not even on the chip, because we could have bad contact on the chip. Okay, so this here is our clock input. Goes to that resistor. Where is that going? Oh, that goes over to this chip here. We need to look up the data sheet for this. I think this chip here, though, is just like an AND gate or an OR gate or something like that. So this is a resistor, and then these two pins hooked up to this disk capacitor. And that makes its way over to there. That might just be a voltage rail, I think. Let's probe around on those pins. So on one side of the resistor, yeah, we're at 5 volts. On the other side of that resistor, we're up at 5 volts, which is pretty much what we see on our clock input, I'm pretty sure. Yeah, 5 volts. All right, here's the data sheet. Oh, I realized I was on the wrong pin. I think I was looking at this pin. I should be looking at pin 10. That's the output that goes over to the other chip. Right here, out C. So there isn't any kind of crystal oscillator on this board. They must be somehow using these parts to generate a clock, I guess, which are these 2 pins right here. So one of them goes to that, it goes to the 5 volts, okay, and the other one looks like it's sort of connected to this disc capacitor and a diode, and maybe this resistor as well. And then there's a larger capacitor that's right there. Hard to tell here, but yeah, I'm pretty sure that this in right here is hooked up to these 3 pins. So a resistor, diode, and a disc capacitor. Okay, so the disc capacitor, this side of it, I mean, this is analog stuff that I just don't understand. So in, out, out. So these are outs. So that goes to that disc capacitor, which should then go to the input. So yeah, this is some kind of like resonant oscillator thing they've come up with. And well, clearly it's either the chip is bad or we have a bad contact with one of these parts, or one of these parts is bad. And then this output here goes to there, which goes to that input, because these are inputs, output, output, input, input. So these are 2 inputs. So the whole thing is like a little feedback circuit. I don't understand how this stuff works. I don't even know what frequency this thing should oscillate at, which then once that runs, that powers up this counter chip, and then that's what makes the keyboard work. So really we have the lack of clock on our keyboard that's keeping it from actually working. So all I can really do here is just check to make sure that all the stuff on what I see on the schematic is actually hooked up to these parts correctly, just in case it's some kind of bad connection. So everything on these 3 pins right here from the body of the chip is connected correctly to the components in the other chip. One of the outputs from this chip also goes to this trace, and that makes its way, oh boy, it's hard to follow this, but I think it makes its way to this right here, this resistor maybe? Yeah, I think it's that one. So I should check that. Yeah, there, that resistor right above the reset key. Okay, actually that doesn't go to that resistor. That goes to this chip and this chip. And it is working. So the little green jumper link that's on here is actually connected properly. So that's good. So I didn't really test it to see if those are good or not. I think that's just another clock signal that goes to these other chips as well. I think one of the, they need clocks as well. Everything needs clocks. Yep, and this other jumper link here, this works as well. So it goes from there to there. Okay, so there's only 2 jumper links there. Well, I'm wondering if that chip is bad. I mean, all the pins in the body of the chip do have contact with the socket and the other things that are around here. I guess I should double check to make sure these diodes aren't shorted that are right here. So they would show up on the multimeter as a short if they were. They are not shorted, nor is that capacitor or that capacitor. So it feels like that chip might be the problem. I wonder if I can test it. I mean, I have the Retro Chip Tester Pro that definitely can test it. I'm looking for my chip remover here. Let's get this out and let's see if, first of all, the TL866 can test it. Logic IC test 14093. It is not found, although the other chip is. This is the one right there, MC14017B. That's the little counter chip. I mean, well, I don't need to test that yet because the problem is the clock is missing. So there's just no way that that counter is going to work. I have no reason to suspect that the counter chip is bad. There's no point to test it yet because, well, it can't do anything without the clock, right? Okay, so let's see. Can this test this chip, the 14093? I wonder if this is the same as a 4093 because Motorola, I think, has weird part numbers. Well, I don't know because the chip, the description for the MC14093 actually says quad 2 input NAND. This says 2 input NAND, 14-pin chip. I mean, it's the same number of pins. This is a 14-pin chip. Maybe this is just wrong. Let's just test this. Oh, it tests fine anyways. Okay. Well, I guess it's the same, and doesn't seem there's anything wrong with this chip. That is kind of disheartening. I'm just gonna put it in the socket and really like wobble it around in there. I don't know. I mean, this is like ultimate penny pinching that's going on right here, to not just have a crystal oscillator that runs this thing and to do this sort of stuff. And incidentally, I assume this can test that. There it is. And indeed, 4093 quad 2 input NANDs. So these are the inputs, 1 and 2, and you see these zeros and ones, and then the H and Ls, that's the outputs. So that would have been able to test it as well. Okay, let's see if this made a difference. No, it did not. Just checking all the pins on this to see if any of them look like they're oscillating a little bit. Does not appear to be the case. Now, you know, I realize the chip is working. I didn't need to put it in the tester, and that's because I know the inputs and I know the outputs. So for instance, that's an input, and that's an input, and those are both high, and then the output should be low, and the output is low. And then this is pin 1, which is an input, high, high, and the output should be low, and the output is low. And now if we go to the one that is supposed to be the clock that goes to the counter, we have low, and we have high, so that means the output should be high. And it is, because a NAND gate, of course, it has to have both inputs high to also be high for the output, but then it inverts the output. It's a NAND gate. So if we have high, high going in, then the output should be low, which is like this gate down here, high, high, and then the output is low. Normally, if it was an AND gate without the N, it would be high, high, and the output would be high, but it's inverting it. So with the clock one, the one that's supposed to go to the counter, yes, so we have low and we have high, so that means they don't agree, so the output is 0, but it's inverted, so that means it becomes high. So everything looks fine. In the state that this thing's sitting in right here, the outputs and the inputs are all correct. It's just there's no oscillation going on at all. There's 2 diodes here. I was going to try to check these. So let's see if these are okay. 0.6, that one's good. And the other one, 0.6, they're good. So those 2 diodes aren't shorted. You always put the black probe towards the band. I mean, there's not much going on here. There's a little disc capacitor. Those don't go bad. There's a small electrolytic. Maybe that's bad. I could take it out and then I could see. So one side of the electrolytic is definitely hooked up to 5 volts. This is 5 volts, like powers that chip, goes down to that electrolytic. And then the negative side does go to one of the, is that an output or an input? That's an input. So it is part of the oscillator circuit. Because yeah, that's one of the inputs. That's 5 volts, input, makes its way to there. The other side of this cap is hooked up to 5 volts, and then it is in concert with those diodes. I guess I should remove it, and we should see if it works. I really don't suspect that that cap is the problem, but let's test it in circuit first, because I really don't like soldering on this. 870 nanofarads. Well, that seems bad. That does seem bad. Okay, I'm going to take it off. We'll test it out of circuit. Yeah, that's can't be right. It's nanofarads. This is 1 microfarad, so it should be 1,000 picofarads. Maybe my math is confused. So this is also 1 microfarad at 50 volts. Let's see what this one does. Oh wait, no, 923 nanofarads. Oh yeah, of course that's right. So I think 1,000 picofarads is 1 nanofarad. And then 1,000 nanofarads, 1 microfarad. All right, well, anyways, I guess what I'll do is I'll install this new cap in here anyways, just to, I don't know. I mean, the ESR was high on the one I took out, but I think the cap is fine, to be honest. I really don't think this is going to change anything at all. But since I already desoldered it and this board, you know, I don't really want to solder on this too much, I'll just put in a new cap. And you know what? Just for grins, let's reflow all of this stuff that's in this little oscillator section, because I am just not confident right now. All right, let's see if this made any difference. No, it did not. I can tell that this is not oscillating whatsoever. So yeah, nothing was wrong with that cap. At this point, let me just turn the computer off. I'm at a loss. I don't know how to make this work, although I just had a thought. Look over here. There's a couple resistors, transistor, you know, there's some part. What if this is the oscillator? Because I did see a signal that goes from here over to this area. Remember we saw that? What if this is the oscillator and it's bad? What if this transistor is bad? Or we have a bad contact over there? So let's turn the computer back on and probe this area and just see if we see any oscillation happening there. Because I thought it was actually like generating over here, but it makes more sense it generates it here, maybe a sine wave. And then that goes over to this, and this turns it into a square wave, which is a much more appropriate signal for digital TTL logic. So let's turn this on and start probing around. First, I'm going to go on this little transistor. There doesn't appear to be anything happening on it. It's high, or it's low, low, high. Yep, nothing is happening over here. Now, there is one of those caps again, like the one I just changed. But usually, I don't suspect it's bad, since the other one was not. If anything, I suspect this transistor might be faulty. So with the computer off, let's do a diode check on the transistor. I don't know which is base, collector, and emitter on this, but that looks fine. Yeah, I don't really see anything wrong. I mean, if it was shorted, I could believe it. So we have a normal diode drop there and a normal diode drop there. Actually, you know what? Taking a look at the reset switch, that goes to that transistor. So this transistor is actually responsible for the reset circuit, and reset works. I should have looked here first, to be honest, but I didn't. So that blows my theory out that the generation was happening over with that transistor on the other side of the board, because this connection that goes over there, that is an input. These three things here, input, input, output, this is just local. And then that's an output, but input and input, that's local as well. And let's look here. So that's ground. These two are joined together. That is hooked up to that. Actually, you know what? It feels like this is the oscillator over here. This really is the oscillator. And it's just something that I don't fully understand. I'm tempted just to feed some kind of a clock signal in here and just see if that starts to generate a clock signal. I don't know what it should be. I could pick a random value like 250 kilohertz and just see what that does. I wouldn't know exactly where to feed it into here, but maybe it doesn't really matter. I obviously wouldn't feed it into any of the outputs, but I could feed it into the inputs of this chip and see what that does. All right, well, I built up the oscillator circuit, and these are the 4 NAND gates, just to kind of see how it's supposed to work. Now, fortunately, this Falstad.com simulator doesn't seem to be able to measure the frequency of the output. So this, I know it's a mess right here, but this output of that gate, that's the clock signal that should be going, that starts the whole thing up. And you can see that it is oscillating correctly. So one side of the NAND gate is actually just connected through a 10K resistor to 5 volts. That is correct. That is connected appropriately. The other side of the NAND gate is hooked up to the output through a 100K resistor, and then there's a 10 nanofarad capacitor. That's the little disc capacitor that's on this board, and that is connected to ground. I have the battery for the power source here. Now, with this thing running, it is oscillating. And you can ignore that there is this 1K resistor here. That's not actually necessary. That was just so there was a little bit of current draw on the output. So I'll delete those since that's not necessary. But this scope right here, this one, is actually measuring this output right here, which is what the gate is. So when this thing goes high, what I guess what does through 100K resistor is it charges up this capacitor, and then that allows this thing to kind of rise up. And of course, with both inputs going high, then the output is going to go low. And then what that'll do is through a 100K resistor, it will discharge this capacitor. So when this input discharges enough, it hits the threshold for this NAND gate and it flips it the other direction and the output becomes low. Well, because the NAND gate, so the output becomes high, and this is the little oscillation thing that's happening. Now, if we view this as a scope, right now it's at 2.056 volts, but the reality is it will be oscillating. So we should be able to take a look at this input on that gate that's on the chip, and it should go up and down around the threshold of this chip. Now, I don't know if we can edit the thresholds on this. Schmidt inputs, does that change anything? We'll stop the oscillation, and this thing is just falling. Oh, there we go. Ah, better, much better. So we speed up the simulation. Maybe this is more realistic to actually how this chip behaves, this particular chip. So now we can see the square wave output, that would be the clock signal, and we can see that trigger going up and down based on the values of this resistor and that 10 nanofarad capacitor that allow this oscillator to work. So I think this kind of kickstarts everything. This goes off to the other chip and everything. Now the rest of this is not doing anything right now, and that's because the input to these two gates, and this is how it's hooked up on the board, these are actually hooked up to an output on the EEPROM. Data line 7, I think it is. So they're using data line 7 to probably toggle these in a certain way. Because if we hook this up to 5 volts like this, that broke everything. We're no longer oscillating. Let's change all of these to Schmidt inputs. Let's think about what happened here. Okay, so I think this value is supposed to toggle. It's not supposed to be stuck, because when this is high, so that halts the entire oscillation, but I guess that's on purpose, probably as a way to stop the clock temporarily. If we remove this, this should start oscillating again. Yes, it is. So while this input is low, we get oscillation, but while it is high, we do not. So this is 5 volts right here. It stops everything. And it also makes this go high. Interesting. Okay, that's the other gate. So that's low otherwise. Oscillation is happening. And if this is high, the input to those, it stops everything. And then that output comes on. So maybe that's like a reset or something like that. Okay, let's scope some of this stuff. So this is the output. And we know the output on this is stuck high right now. And then this pin right on the end, this is the one that is affected by the output. So that's this one. And that is currently just high, stuck high. But I think that's correct because this is stuck high and therefore it's going to charge that cap high. So that's just all going to be high. We're not going to get that like 2.5 volts or whatever, you know, that up and down oscillation. And that's because this other input, which is this one here, which is connected to these 3 components, both diodes and that resistor, both diodes and resistor, it's this trace right here. It's noisy, it's actually low. But for the oscillator to run properly, this needs to be high, not low, it needs to be high. Now the reason why that is low right now, I think is because, well, let's see, if I draw a wire from here to there, that is what's going on. So see how that made that input low, and that stops the oscillation, and it makes the oscillator's output high, which matches what we're seeing. So these inputs here to those gates, if we could bring back GIMP, what those are these. Those are those and those. These are all common together. And then see this trace goes off here, off to somewhere else on the board. This ends up going right here. It's pin 17 actually is what that is. And if we take a look at pin 17, that is data line 7. Now remember, the keyboard interface in the Apple II is 7 bits, so it doesn't use this top bit here. Q7 is not used. So my assumption is if we look at that output on pin 17, I assume it's just going to be stuck high. So here's 13, 14, 15, 16, 17. It's 4.2 volts. So when this is high, the oscillator is not running. Right, okay, that makes sense. So what's going on? Let's look at the EEPROM here. It looks like every single value in the EEPROM is 7F. And to me, if we type in 7F, that is not high. Data bit 7 is low. And there's data bit 7, it's that one. And that is low. So why is that outputting a high right now? So yeah, some of the values on the EEPROM are high, see like AE, C3, but it depends on what is going into it. So we need to take a look at all the address lines going into the EEPROM right now because the whole thing is just stuck. Let's look at those address lines and then let's see what value that corresponds to see why the output is high. Okay, so we have address lines 0 through 11. That's all that's on this EEPROM. And I'm just going to go through them. I won't bore you, and I'll write down the value of every single one of these. All right, so we have everything low except for address line 2, which is high, which is what I'm on right now, is pin 6. But the weird thing is, oh yeah, it matches. Okay, so that is definitely high. Don't know why that's just sitting there high. And that gives us hex value of 0, 4. And that's 0, 1, 2, 3, 4. It's 7F. And 7F does not have the output pulled to high. So I don't know if this is like our EEPROM that's bad or this is like a bad connection somewhere. Well, let's take a look at all the data lines while we're here. I didn't look at those yet. Oh, 9 is high. 10 is the 10 is high. Data line 1. What's going on with this EEPROM? Okay, so everything is high coming out of the EEPROM right now. Remember when we tried to read the EEPROM and it showed up as all FF? I'm just going to make a new EEPROM. I have what looks like a good dump, I think, of the EEPROM. I think because of this corrosion that's on this one, I'm just going to make a new one from that image that I got off of this and hope that that makes a difference, because this thing looks like it's outputting FF right now on every data line. And as far as I can tell, when this is outputting a 1 on data line 7, that stops the oscillator. So let's switch this over to Intel, because this is what my blank chip is, and we'll load this again. And let's program this Intel 2732, and hopefully this will output the correct thing. And then maybe, just maybe, we'll have a keyboard that's actually oscillating. Okay, new EEPROM is programmed and it's in, and I'm going to go right to pin 17 before I turn the computer on, and we're going to look at what the output is. All right, remember, we're looking for this to be low. Look at that. It is not just stuck anymore. So does this mean our oscillator is actually working? Let's take a look at the output. Yes, it is. There it is. It was the EEPROM. Well, I'm really feeling lucky that I was able to get a good copy of it. Do we have a functional keyboard now? That is the question. Oh yes, the F key works, so H is not working. Okay, so we probably have bad switches in here or other issues. So this keyboard's working better than I thought it was going to work, but there are still issues, and I don't know if the problem is the dump of the EEPROM that I got was bad, which is entirely possible. That could be responsible for the fact we have like columns that don't work, and then we also get some keys that work, but they're giving us a space, and the space bar does actually work, but like enter doesn't work, and I mean a bunch of stuff doesn't work. What about the repeat key? Oh, repeat key works fine. What I have noticed though is that the 4 key works, and so does 5, and I think that's enough for us to boot that diagnostic software. Oh, I cannot push enter though. What about M? Oh, M works. Control M? Yes, I can hit Control M. So that'll be my way to push return. So I think on the color test, which I really want to see, I think I have to hit 4 and Control M. And that should work, maybe. Disk controller's back in. Let's boot up the system. It's nice to see the motherboard is still working. Other tests, 4. Control M. CRT test, good. Q is a key that works. Control M. Color bar pattern, 1. This is what I wanted to see. Oh, look at this. So as far as I'm aware, even on a Rev 0 version of the Apple II, you should get all 16 colors. And yet for us on this motherboard, we're only getting shades of purple and green. How interesting. You know, so turning color trim, that does not bring back our colors. And turning this other trimmer over here also will not bring back our colors. If anything, it's going to make them disappear. Yep, they're gone there. Right, so color's bad. I kind of knew that. We definitely have a problem with the color killer circuit on the motherboard not working, plus the color itself is screwed up in a weird way. I've never seen any kind of issue like that before. But the keyboard, which has signs of life, which is great because I feel like I made progress, we clearly have issues on it still, and I would really like to get it working. As far as I can tell, all of the switches, or most of the switches, actually work. I mean, it's hard to know with these columns, but we either have broken traces, but more likely the dump from the EEPROM that I got originally is bad, and that's why we're missing entire rows and we're getting those spaces, or we have issues with like the socket or some other problems on here still. So I need to put the color and the video issues aside for now and get back to fixing this keyboard. I didn't know this was going to turn into a keyboard repair episode, but here we are. All right, so I started to poke around on the keyboard, the backside, and I've got to say, working on keyboards is pretty miserable. If you have the schematics, it's one thing, but just having your multimeter on continuity mode, that does a lot. And I think I've figured out at least one problem. When you look at these things on the back, one of the things you always want to suspect are these little green jumper links. Now, all they're doing is just connecting, for instance, like this one here is connecting from there, if I get my probe on it, to this. And see, it's like 2 ohms. They shouldn't have any resistance. I mean, there's going to be a little, that's not a big deal, but they shouldn't have any. So I started checking around with these links, and I found one that looked suspicious. I'm just going to check this one since I have my probes on it. 2 ohms, so all fine. Well, we have at least a couple columns that aren't working kind of in the middle of the keyboard, and there's one that sort of, some of the keys give a space, and I don't know. There's multiple problems, I think, going on here. But at least for the two that are bad, they end up going down to these diodes. So the bottoms of the columns connected to these diodes that go all the way along the bottom of the board, and then those make their way back up to the top. Well, these two rows, like this one here, ends up going through this diode, and then that diode is connected to this diode, so this next row is connected to it, and then it's connected to one of these green jumper links that then makes its way over here. So if I'm going to go on, you know, the bottom of, or this diode right here, which goes across this link, and I follow this over to where it goes, well, see at the multimeter, it's like 4.1 K ohms. So that link is bad right here. So I should just jump over it, and I think that might partially repair some of the keyboard. But it's worth checking some of these other ones while I'm at it, and I'm just going to have to kind of go through the whole board, check them all, and find any other ones that are bad. And then all you have to do to jump over them, because you can't really solder, you know, where they are, you just, you know, go to a nearby solder joint and then run a bodge wire to wherever the trace is going. So there should be another through-hole solder point somewhere else, and you just bodge over it. So I'm just going to spend a moment and kind of go through these, and what I'm going to do is I'm going to grab a marker so I can just put a little dot next to the ones that I test that are good, so that I know I don't need to try to jump those or whatever. Okay, so I found two that are bad, these two, the one that I already showed and the one right next to it. But all these other ones seem to be good. I didn't check everything up here, but there are a couple odd things on this board. Look at this. That's got to be on purpose, I have to imagine. These two traces do make their way over to the EEPROM though. I think it's like that one and that one. These two green things right here, those go over to here. So I'm going to bodge these two, but if it doesn't seem to work, then I suppose I can reconnect those. Because like those traces, I mean, they certainly seem like they go to a bunch of stuff. This one here goes to a diode. Well, it's cut, like it will never make its way back to the EEPROM, but that makes its way over to this area here. Yeah, I don't know. I don't know if that's because this is a 4K EEPROM to have like other character maps, maybe, or something. Just that looks on purpose. I don't think that was on by mistake. Let me bodge these two connections, and hopefully that fixes the majority of this keyboard. All right, two bodge wires. Let's do a test, see if we have more keys working. By the way, I think the reset circuit is messed up somehow. Yep, something's going on with the reset circuit. It kind of wakes up once it's powered up for a little bit. Okay, QWERTY. No, we do not have additional working keys. Wow, that did not fix it. I was sure that that was the problem, but there's no actual improvement at all. Spacebar works now. I think that's new, but enter doesn't work. Yeah, but we still have just as many bad keys. Very worried that the EEPROM is our issue. I'm surprised that there is no visible difference. I think spacebar did not work before, and that does work now. So that's the only difference I actually see. Now, in case you're thinking that perhaps I need to redump this, I actually did do more sanding on the pins, and one of them was broken because it was so corroded. So I stole a pin from this bad EEPROM, soldered it on there, put it into a flat socket because this actually potentially gives better contact, and I'm able to make reads from this, but the read I'm getting out of this is exactly the same as the read I got that's on this chip right here. So there's no difference between what I read off of this and what's on here right now. So we still might actually have a faulty read on this chip. Now I just had a thought. What about those cut traces? I totally forgot about them. Should I bodge over those? I might as well. Let's just see what that does. I don't know, maybe that cut shouldn't be there. All right, I'm just bodging these on, and you know what's funny is this bodge wire which I added, this actually goes to one of the cut traces. So maybe that explains why putting that bodge didn't change anything. All right, so it now is bodged from over this bad jumper thing to that diode, which goes to some other stuff, and then instead of this cut trace, which is where it used to go, it now goes to the EEPROM directly. And that used to go over that jumper link on the second trace here through there where it's cut, around here, all the way to that diode. Let's see what this does, if anything. No, that did not, that did not fix anything. Oh, well, it did. T works now. Y works. Oh, hold on a second. We have a lot more working keys than we had before. Now, finally, some progress here. Oh, and enter works too. What about the shift key? Shift is working. A, S, D, F, G. Okay, H is not working. J doesn't work. Okay, so we have something going on this row here. Maybe there's a bad connection or something as well. Yep, and arrow keys. H, J, K, L, plus sign, and left arrow. Those all don't work. And then on the bottom row, yeah, so that cut should not have been there. That should not have been there. Both shift keys are working. And let's check the numbers. Unbelievable. Yeah, this thing is working so much better. Enter works as well. Why was there a cut that looked so deliberate right there? Well, a couple things. I'm relieved that the EEPROM is not the problem. I mean, obviously the original EEPROM is dodgy, so I'll just use this new one, but I'm glad I was able to get that good dump off it. What does the caps lock key do, if anything? Nothing. That doesn't do a thing, which is not surprising because this computer does not have lowercase on the character set. And yes, I did dump the character ROM and looked at it in the font editor. There's no lowercase at all. All right, well, this is excellent news. So let's see which is not working. So all of these keys are not working. All right, let's trace this out. So this is the left arrow, goes to there, to there, to there, to there. Okay, now how does this connect up to the top? I think these are all the bad keys, all in a row. So it goes through this diode right here. Let's see if the diode is good. I mean, I can't see the diode. It's on the opposite side of the board. And sorry about all the glare. You just can't see anything, can you? Let's see if this diode is good. It is. But let's follow the trace. It's like going underneath all this garbage here. Goes to there. Okay, so this could be a bad connection inside this chip. This, I don't know what that chip is doing, but I bet you we just have a bad connection on that pin. It's this one right here. I should probably push on it while I type to see if those keys come back. So let's break out of here. Okay, not working. There it goes. Yeah, bad connection. Yes, okay. Troubleshooting. All these keyboards work in a very similar fashion, so you just have to kind of work methodically through everything. What's amazing to me here is that all, and I mean all of these switches are good. Considering how dirty and oxidized everything was, I just put some stronger deox of the D100 on here. And I might be able to change out this chip if I need to. Maybe I'll use a little sandpaper on its legs. I just had some sitting off to the side there because I was sanding the EEPROM. All right, so it seems like the 4 switch is a little dodgy. I got like a couple bounces there. Yeah, we're up and running. Everything works. Escape key works. I can move the cursor around. Repeat works. That's perfect. Enter works. Reset works. It totally is fixed. It is totally fixed. This keyboard is so rotten looking, and yet it works. But we had to do all this to it to make it work. What is the deal with those cut traces? That really looks like someone did that on purpose. Was this sabotage? I just don't know. But too bad of these cheap jumper link things and 2 cut traces and bad contact in that socket and the EEPROM, which is not making good contact. I presume if I really clean this up, maybe it would work again, but I think the oxidized socket plus this oxidized chip just equals something that doesn't really work. But on its own, this keyboard works. It's just dirty and nasty. Yeah, it's pretty nasty. So I spent a little bit of time cleaning up the keyboard. I cleaned all the dirt that was off the keys, and I also applied 505 aerospace protectant. It's kind of like a, well, plastic rejuvenator, just makes the keys look a little nicer. Now they are a little shiny right now. That'll dull down over time. I just applied it a little bit earlier today. But there's something else you may notice. Here's the space bar. Notice it works now. It originally had a broken stabilizer on the left side. This is it. And I actually took it out of the board so I could measure it, and just taking it out actually broke one of the clips off the bottom. But it didn't matter because it was already broken. And I went ahead and designed and 3D printed a replacement. So there were 3 iterations. This one didn't really work. These 2 parts that go into the base plate were too far apart. Same on this, but I made the clip a little bit bigger so it holds the stabilizer bar. I had to break off one of the clips so I could test fit it. And then the final one is this one. So this is the one that's in the board. It clips down into the base plate, and then the stabilizer bar hooks on to the little hook area. And as you can see, works freaking perfectly. I also spent just a little bit of time with the hot glue gun just to hot glue down these bodge wires so they're not going to go anywhere. And I have decided to not use the original EEPROM, and I just use the replacement one. So I put a sticker over that and just put a date on there when I actually service this thing. And now that the spacebar is working and I boot it up into BASIC, and it really actually is a pretty good keyboard. I think the switches this uses are the same as the really common switches that most Apple IIe's use. Early Apple IIe's, you could get them sometimes with Alps switches, and I have a couple machines that are like that, but the majority have these switches that are all black in color and they have a cylindrical slider looking mechanism. That appears to be what's on this keyboard. So it feels not amazing, but it feels a lot like an Apple IIe. I don't know if they're 100% compatible, like I could swap one of these with a IIe switch, but generally all of these switches are actually working fine. I think number 4 sometimes bounces a little bit, but every other switch appears to just work perfectly. And that's frankly pretty amazing. Obviously a lot of like junk has fallen down along the top edge here, and that's what damaged the EEPROM, like it made that pin fall off, for instance. But the fact that all the switches are working and they feel okay to type on is a testament to the quality of whoever made these switches. Some of the keycaps do have some of the legends rubbing off, but these are not double shot and that's just printed on top. So it's just how it goes with these cheap keycaps. Now I did discover a couple cool things about this keyboard that I'm going to talk about that are a little bit of an improvement over the original Apple II Plus keyboard. But before we power up the computer, there's definitely something going on with that reset circuit, and it seems to go away after you first power on the machine. So I want to investigate before I power this on because it's been sitting off for quite a while. And I did a little bit of reading in the circuit description, and I was thinking that this was the reset circuit, this 555 timer, and I was sort of poking over there. Turns out that this is the reset circuit. It's another 555 and this transistor. So how this circuit works is just extremely simple, just a 555 timer, and we have a transistor with a 1K resistor, and when this is activated, it just pulls the reset line down to ground. Otherwise, the reset line just floats. I'm assuming somewhere on the schematic, it doesn't show it on this page, is a pull-up resistor, so it'll be pulled to 5 volts. Now the keyboard reset switch also just goes to that same reset line, and when you hold down control and reset, it just grounds this reset line. So that ends up going to, various things like, oh, there it is. There's the keyboard connection, actually. It ends up going to the CPU and whatever else, the slots and stuff like that, I think. It's my hunch, because based on the symptoms we heard where it was sort of making the beep going like really quickly, I have a feeling if I clip onto the collector of Q5, then we scope that. When we turn on the computer, we're going to see that reset line either kind of hovering in the middle or bouncing, or something weird is going on. But the weird thing is it does go away and then the computer just works fine after that. And on this particular design, it does say EBC on this transistor. So let's clip right onto the collector because that's what we want to measure. Oh, by the way, here's a 3D printed part. I just had Cura open still on my computer. So that's the little stabilizer bar thingamajiggy. I'm going to make a GitHub repo for this computer that's going to have a picture of a motherboard, and it's going to have the ROM dumps along with the keyboard ROM, and I'll upload this little STL file if you have one of these keyboards and you want to make a new stabilizer. Okay, so we're clipped on right here to the collector, which happens to be what goes to the reset lines of the CPU and everything like that. And let's turn on the computer. Here we go. 3, 2, 1. Well, that looked fine. It just... See, the computer is doing that weird oscillation thing right now. What's weird about that to me is this is the transistor that actually is generating the reset. And why is the CPU doing that? Unless like there's a bad connection in the CPU socket for the reset line. What I'll do is I'll turn this back on and I'll demonstrate when I push Control Reset on the keyboard. See how it makes it go low? But it was still struggling there. I heard some weird like buzzing out of the speaker. That still implies the CPU, is having an issue. Okay, here's the reset line on the CPU, and there is that pull-up resistor, and it's definitely being pulled up. We could see that on the scope, but I guess I need to take a look at pin 40 on the CPU itself. And I guess I just have to hope that me poking it doesn't cause it to come good, because it's quite possible anytime you have like bad connections in a socket, just probing stuff potentially will fix the issue. So I'm not going to push too hard on it. Hopefully I'm making good contact. Here we go. Okay, yeah. So notice how it was sort of falling there. Now I'm going to do the same on the socket itself. And be very careful not to push on anything too hard. We could have a bad connection here, everyone. I might have to make another bodge. So I'm on the socket now. Well, and it seems like it's just working. I'm not getting that weird buzzing noise. Oh, but the CPU is still weird. Okay, I'm going to push on it. Okay, I think we just have bad connection on the CPU. Well, specifically on that reset line. Now, I'm pretty sure I had the CPU out, I think. Oh, wow, it's tarnished. It is so tarnished. So, yeah, this is the reset line right there. Notice it's looking pretty nasty. Let me get some sandpaper or just lightly sand both sides of the CPU. Okay, I'm not looking for perfection, but it's certainly better than it was. Let's see if we have it actually all the way at 5 volts. 3.8, not great. What about the socket? Oh, same. Okay. Let me just see. Oh, there's that same issue right there. It was just doing it. Turn this off. Well, now the computer didn't even reset. Why? Oh, wait, this doesn't make sense. What's happening? I wonder if we have a clock issue, maybe. Here is our clock. I'm on 39. I don't know which one this is. 37, 39, not connected. Oh, that's Phi 2. That's an output from the CPU. This is the input that goes into the CPU. I mean, that looks completely fine. But why is the machine not out of reset right now? This is weird. Control reset. What's happening? Look at this. Our old friend, the white screen. Oh, this is hilarious. We're back to where we were. Okay, wait a second. I'm moving the power connector and it's doing that. That didn't actually fix the computer though. It just made it look like it did with the question marks. Wow, we are stuck. The computer broke. It just re-broke. I have to admit, I didn't expect this to happen. I pretty much thought that this machine was fixed and I was getting close to the end of this repair series. Let me try turning it on again one more time. Yeah, it's just, that's it. Nothing. We're basically in exactly the same spot we were before. I'm scared that we have a potential bad trace, another one that's showing up on here. And I mean, we know those are super hard to find. The last one I fixed was under one of these chips. I honestly forgot which one it was at this point. And wow. Now, one possibility, and I didn't really talk about this before, is if you do have a bad trace that's just sort of marginal, just sort of bending the board a little bit. I should have left the keyboard hooked up, and resetting the machine might bring it back, but that didn't do anything. So I'm going to try to bend it this way now. That didn't bring it back. And we are just getting the solid white screen. So we're back to basically the machine just not showing any signs of life right now. And if I take a look on the socket itself, because I mean, that's what I did touch, right? I sanded those pins down on the CPU. This is on the socket, and we see stuff. If I didn't see stuff there, that's what I would be worried. Okay, what about this one? When I turn it off, it sort of appeared. Okay, no, it's there. Oh yeah, there we go. We're on the socket. This is checking for bad contact between the CPU and the socket. Okay, this one is just sporadic, but it's doing stuff. I mean, I'm gonna have to break out the diagnostic ROM again, aren't I? Yep, so far so good. 22, 23, 24, 25. And then we're on 26. This is a data line 7, 6, 5, 4, 3, 2, 1, and 0. All the data lines on the sockets are doing stuff. Let's look at pin 7, the sync pin. There's the sync pin, which I think people explained to me. This says that the CPU is doing stuff. It's not used on the Apple II, but if the CPU is executing code, you actually see activity on here. And I mean, we do. We see activity. All right, so with that, this video has been 1 step forward on fixing the keyboard, great, but 2 steps back because what I thought was just a simple problem with the reset circuit turned out to have totally broken the computer again. What I was about to talk about with the keyboard is that it actually has some improvements over the original Apple II keyboard. So normally with the Apple II keyboard, you can do Shift-P for the @ symbol and Shift-N for the tilde. But this keyboard actually allows you to type both square brackets, so Shift-M and I think Shift-L, or maybe it was Shift-K. And you can also type the underscore, which normally you can't type on the Apple II. I think that was like Shift-L, or maybe it was Shift-O. I can't remember which one it was. And you can also type a backslash. One of these keys over here gives you the backslash symbol, which is also something you can't normally type on the keyboard. So this keyboard, through the little ROM that's on here, does support typing those extra characters. Now, I did test on a clone I have up in my office. It actually supports the identical shift key combinations as well. So that's kind of curious. Otherwise, after the repair on this thing, this keyboard was working perfectly. No issues whatsoever. So I guess when I get the motherboard fixed again, then the keyboard is ready to go. We still have other issues with this board. Of course, the main problem being the color, which we saw earlier in this video. Everything is really green and purple and shades of those, so that's not right. And we also have that spurious black line on the left side of the picture, which causes the auto gain on something like at least the RetroTink to be screwed up. But I think that would also affect a CRT similarly. Color CRTs would probably also be affected. Oh, also we don't have the color killer circuit working. There's really no point in me trying to troubleshoot the color killer problem or the color issue until I got this computer working again. I wonder what's broken this time. Put your guesses in the comment section. There's obviously going to be a part 4 where I try to get this thing working again. You know, this is a problem when you have these machines that have all these chips that are in really dodgy sockets, but then we have motherboards that are low quality, unfortunately. I mean, I have to say it. We already had one bad trace. I guess we have another one on here. So now I'm going to have to kind of root around and get to the bottom of what other trace has failed on this, causing this kind of issue. This is just like the other clone. It's just like the other clone. Same problems. It's so weird because you have to wonder if these bad traces were a problem back in the day, or if this is just a function of time and corrosion. That other machine that I have up in my office had also been exposed to a ton of moisture and corrosion, and maybe that just eats the traces away. I don't know. All right, well, if you've enjoyed this video and this repair series, I'd love a thumbs up. I hope people aren't getting burned out on me working on Apple IIs here, but I do love working on them, and they are challenging because there's so many chips and we have so many connections and things that can go bad. Think about how many TTL logic chips are on here, and each one of them is like 7, 8 or more pins on them. And each one of those connections, you know, everything has to work right for the thing to work correctly. So there's a lot of opportunity here, especially because it's all socketed, for things to go wrong, and they have done exactly that. Thank you to my subscribers, thank you to my supporters, names go off the side of the screen to make it possible to do this full time. And I guess that's gonna be that. So sorry, I was hoping for a win on this video, and I guess I had one, but now I have a 2 steps back kind of situation. So stay healthy, stay safe, and I will see you next time. Bye-bye.